Today, I'm going to be talking about update strategies for edge devices. This can be a deceptively difficult problem to solve for, especially if you're dealing with a fleet of devices with different capabilities, but there are some tools and design strategies we can implement that address a number of these pain points. Before we get started, a little bit about me. My name is Kat Cosgrove, and for about a year, I was an engineer on JFrog's IoT team before moving into a developer advocate position. And our goal is to bring DevOps to the edge because it should not still be this difficult to update these devices. And in pursuit of this goal, we found a lot of interesting solutions that we could bring into a CI/CD pipeline for embedded Linux devices, and eventually built a pretty flashy proof of concept that put several of these solutions on display. First, let's get a little bit of context. Just how large is the edge? How many devices are we talking about here? If you count both dumb sensor edge devices and smarter ones or gateways, we're looking at around 20.4 billion edge devices today. It is a lot, yeah? So how are they being updated right now? Some of them can't be updated. They are throwaway devices, effectively single use. When they break, they need to be replaced. Talking about things like the old Fitbits and whatnot. A lot of those that are being updated do it in a way that's kind of unwieldy. It's time consuming, or the infrastructure to support it is complicated, or it can't happen wirelessly at all and requires physical access, which is either expensive for the manufacturer if they have to be the ones to do it, or it's irritating for the user if they have to do it themselves, and sometimes confusing for the user. Like, not everybody is comfortable with that. And I personally don't need more cables laying around my apartment. I don't know about you. But in spite of the fact that things are annoying or cost a little bit of money right now, the industry is still booming. It's taking over larger and larger shares of all kinds of markets. So why should we spend the time and effort to change something that is maybe a minor inconvenience? It is beyond a minor inconvenience. Our lives are increasingly reliant on edge computing and IoT, with devices taking over larger and larger amounts of work in consumer, industrial, retail, and medical spaces. And people don't want to spend lengthy amounts of time waiting for a software update to complete, and they definitely don't want to have to plug a device into a computer to do it. It's also really dangerous. Infrequent or non-existent software updates, regardless of the reason for it, makes edge devices a serious security vulnerability in anybody's network. Everyone knows that unpatched software is a problem, right? So this could mean anything from the exposure of user or client data to a malicious third party, to devices being harnessed for a botnet or cryptocurrency mining. This has already happened on a wide scale, and it's continuing to happen today. Just a few years ago, a whole bunch of people's smart appliances, refrigerators and whatnot, got harnessed for a botnet being used to DDoS services, which is insane. And the safety implications for medical devices are even more concerning. So what is slowing us down? What's preventing us from fixing this problem? We've acknowledged that it's an issue. Why aren't we fixing it? We flat out are still not building for it. We know it's a problem, but we're still not thinking with not doing this in mind from the get-go. A lot of edge devices are still just simply not designed with the ability to be updated. They expect to run the software version they ship with until they break, and the update strategy for these devices, if there's one at all, is just flashing them. That's dangerous because how often do you write a piece of software with 0 bugs in it? How confident are you in your QA team to find every conceivable edge case? You should not be that confident because on average, there are between 1 and 25 bugs per 1,000 lines of code. bugs are making it into production. Do not gamble on your code being perfect. We also have to deal with some connectivity concerns with edge devices. We can't really rely on the device's network. The network hosting the device might be unstable, the connection could be intermittent, the speed of the network might be really slow, so we need to keep the update as small as possible, and it probably isn't a secure network either. So these updates need to be signed in some way so they can be trusted. It's also just a whole hell of a lot of devices. There's a lot of hardware variations. Those 20.4 billion devices are not running on anything standardized. Each class of device is running on something specialized with differences in available communication protocols, memory, storage space, architecture, and operating system sophistication. So how do we design a system that takes these differences into account and handles them, allowing for easier deployment to broader classes of devices instead of just a single board or device type? Can we have a one-size-fits-all solution for a market that comes in a lot of different sizes? Probably not, but we can get us something like one-size-fits-lots. So to drive this point home, we built a proof of concept using the most tangible example of an edge device we could think of, a car. You might not want to think of a car as an edge device, but these things are basically data centers on wheels at this point. There are 3 or 4 computers in most modern cars, handling a lot of the driving and workload. That's beyond your infotainment system, too. We didn't use a real car, obviously. We didn't have the budget for that. We used a Raspberry Pi 3B Plus strapped to a remote-controlled car. People get to interact with it in one of 2 ways: by driving it, as you can see in this picture. We have a wheel, race wheel made by Logitech that's meant for like racing simulator games, connected to a NUC that's sitting under the seat, and that's communicating with the board on the car. Or you can interact with it as a developer, pushing updates to the car while someone else drives it. We allowed real randos off the conference floor to write and deploy real code to the car. That's how confident we were in the tools we used and the system we built. The car was also capable of driving itself, and the driver could choose to record their laps to train the existing driving model, but that wasn't so much a part of the technical demo as it was just like a cool, fun thing for us to put in for pretty low effort, because self-driving cars are cool. So how does it work now? The overwhelming majority of cars are not designed for over-the-air updates. Teslas are, and so are a couple of others. A couple more car manufacturers are working on it, but the vast majority of cars need to be brought into a service center for updates, and that can take hours. Even the cars that do handle over-the-air updates now, some of those are still like pretty lengthy, and you can't use the car while the update is going on. And that, is kind of inconvenient. Different cars are also using different boards and running on different operating systems. So even within one corner of the market, there isn't really any standardization yet. Also, 15% of vehicle recalls are a result of bad software that needs to be updated. For example, Jaguar famously had a recall like a year and a half ago for the I-Pace, I think, to fix an issue with the braking system, and that was a result of bad software. Another car stranded its owner in the vehicle on the highway for hours because it could do over-the-air updates, but a bad one couldn't be rolled back. So this was a very real, very painful, and very potentially dangerous issue that presents a range of solvable pain points for both the end user and the manufacturer. The combination of these issues in one single device made it a great example for proving that we don't have to do things this way anymore. And because we were working with a car, we were very motivated to make this update happen quickly, reliably, and without the potential for injury to the user. So when you're dealing with, several thousand pounds of moving metal, injury to the user can mean killing the driver or killing a random pedestrian, and that's, not good. So the workflows and tools it took to make this happen, we had two distinct workflows showing off two distinct strategies for the proof of concept. For one workflow, we just updated software running on the car without flashing its firmware. It's very quick, it doesn't interrupt the user, and it supports rollbacks. This workflow relies on K3S and Helm. For the other, we updated the firmware itself in just a few minutes with the ability to automatically roll back if a fault is detected. This one relied on Mender, Yocto, and Artifactory. All of the updates are scanned for vulnerabilities using Xray, and pipelines can manage the triggering of different events. Let's take a look at the software workflow. This is just a quick overview of the technologies at play in a workflow for software updates. We used JFrog Artifactory to manage and store our various build artifacts, as well as handle promoting builds from development to production. Xray is used to scan our package dependencies before release, giving us detailed information about any vulnerabilities or potential policy violations. And K3S and Helm are used to deploy to the car. Since it already integrates with JFrog products, JFrog pipelines would be used to orchestrate all of this. Let's take a look at some of these tools. So JFrog Artifactory, for those who are not familiar, is a universal binary repository manager that automatically manages your artifacts and dependencies through the application development and delivery process. It supports a ton of packages right out of the box, like Maven, PyPy, NPM, Go, etc., plus a generic repository type, which we use later on. And if you want to, you can use it as a private Docker or Helm registry too. Artifactory integrates with whatever your favorite CI server is, and it also includes a pretty robust REST API, so it's easy to use alongside your existing tooling. JFrog Xray is my favorite. It is a tool for continuous governance and auditing of artifacts consumed during your pipeline. It contains a very large amount of data about known vulnerabilities, and it can scan any binary and package type, really, if it's an Artifactory, Docker, Java, NPM, whatever. And it ensures that what goes into your builds and your releases doesn't contain any high-risk vulnerabilities or license violation. You defined what high risk is to you through a system of policies and watches on different packages and repositories. Xray's main source of data for these vulnerabilities comes from Risk-Based Security's VulnDB, which is the most comprehensive vulnerability intelligence database out there. Basically, if there's a vulnerability that's known, whether it's public or private and known only to risk-based security, you're gonna hear about it. We also relied on K3S for this. It's Kubernetes, but 5 less, which is just the cutest open source project slogan out there. I love it. It's just lightweight Kubernetes designed for edge devices. The binary is only like 40 megabytes and it uses like 512 megs of memory. It's got very, very minimal OS requirements, which means it's great for the edge. And its required dependencies are just containerd, flannel, core DNS, CNI, and some utilities like IP tables and SOCAT. It's also wrapped in a launcher that abstracts away some of the more complex issues like generating TLS certificates for secure communications and setting some other options. If you've never used Kubernetes before and you're scared of it because you've heard that the learning curve is steep, it is. It's real steep. Kubernetes can be terrifying. K3S is way easier to use, I promise. There's still a learning curve for sure, but it's not nearly as rough as at least I found learning Kubernetes for the first time to be. We also relied on Helm, package manager for Kubernetes. If you've ever used Kubernetes, you're probably familiar with this. but it uses charts to describe complex applications, makes it really, really, really easy to install and deploy. The charts serve as the final authority on what your application looks like, and they are also super easy to version and support quick rollbacks if something does go wrong. This is part of one of the Helm charts we used for the demo. It's building the microservice that handles the controlling of the miniature car with the racing wheel from the picture earlier. The syntax here is pretty simple. It's YAML because this is DevOps, so of course it's YAML. And using these two tools made the updates to the applications running on the car fairly quick. The average amount of time from a developer pushing code to deployment on the car was about 35 seconds with no interruption to the user at all. It can happen while the device is in use. That's not to say that it necessarily should happen while the device is in use and without telling the user. For most updates, I think that there should be consent from the user involved, or we should at least tell them that it happened. Shouldn't happen silently. But if you design your edge device with this strategy in mind, it does mean that you can update silently. For edge devices without any user interaction at all and no need for a full firmware update, this is a pretty compelling option. If I was in the mood to just over-engineer the hell out of a personal project at home and I didn't ever want to have to deal with interacting with it to push an update, this is probably what I would do. Next up is the firmware workflow. This one's a little more complicated. Similar to the software workflow, this is an overview of what happens. Yocto is used to create our builds. We have pipelines handling all of the events again, and Xray checking our packages for vulnerabilities again. We're also using Artifactory again, but in this time, for a little bit more than storing binaries. It's handling some of the workload for Yocto, storing its build cache to make things faster later on. And we are using Mender to handle the over-the-air deployment. Mender is over-the-air updates for embedded Linux devices. It ticks several of the boxes we're looking for. All of the updates are cryptographically signed and verified. It supports automatic rollbacks to a previous version if a failure occurs, and it allows for several different installation strategies, but I'm going to focus on the dual A-B strategy. Using this method, two partitions exist on the device, A and B. Duh. The bootloader is aware of which partition is currently designated active and which one is not. During an update, the new firmware is streamed directly to the inactive partition, and at this point, the partition running the update is designated active, the old one is inactive, and on reboot, the bootloader starts the new partition. Because the partition running the older software still exists, although it's designated as inactive now, Mender offers us an additional layer of security. If there is an issue with the new build that wasn't caught in earlier testing and prevents it from booting correctly, Mender can automatically roll back to the previous version by switching to the inactive partition. So the use of Mender's dual A-B strategy alone adds a lot of additional speed and security to your edge deployments. The update can happen in the background without interrupting the user at all, and then in the case of a car, the next time the user turns on the car, the new update is there, and maybe all they had to do is approve it, say, yeah, give me this new version, and it happened while they were driving. But we still have not addressed the issue of the size of our builds, which is a problem with edge deployments. Enter the Yocto project, providing custom Linux distributions for any hardware architecture. Yocto is really cool. It drastically reduces the resources used on your board and minimizes your hardware requirements by allowing you to build a custom distribution without certain modules that are unnecessary for your particular hardware. So say you know that you're only going to need to communicate with this device over Bluetooth, but there's an Ethernet port on board. You can build a Yocto recipe that does not include the module for Ethernet. It uses BitBake to write recipes for your build, and you pull in layers for different hardware configurations and applications. We used a layer for the board itself, which was a Raspberry Pi 3B Plus, as well as layers for K3S and Mender. They provide a ton of these hardware layers for common configurations, so you can get started really, really quickly with this tool. And if you want to, you can also write custom layers to isolate specific applications or behaviors. As an example, this is part of the meta layer that adds K3S to our Yocto build. It's pretty straightforward, and it allows for the execution of both Python and shell scripts in parallel. Anybody should be able to pick this up pretty quickly. Anybody who's already an engineer, at least. So the first build is going to take a while, but we can speed things up drastically in the future. Yocto caches everything it downloads during a build, which does allow for incremental updates. If you have it use this build cache, at least, it's only going to rebuild what's changed. So this is where Artifactory comes into play. We can use a generic repository to store the Yocto build cache and tell Yocto to use that during future builds. Doing this alone reduces the time required to build by as much as 50%. It's a pretty significant difference in build speed. So the result of this is that using Mender to handle deployments and Yocto for our builds while pulling the build cache from Artifactory, the time for a full firmware update was between 5 and 10 minutes after the first build. That's 5 and 10 minutes that the user doesn't notice, aside from saying, yes, I would like this update, pretty much. The build is as small as we can get it, so we've minimized potential issues with low bandwidth on the device's network. The updates are signed because we're using Mender, satisfying a security requirement, and automatic rollbacks are in place in case of a failure. So we have succeeded. Let's recap. The way a lot of Edge and IoT devices are being updated now, if at all, is broken, and it badly needs to be addressed. It does not have to be this way anymore. We have the technology available now to handle some of these problems. For Edge devices running embedded Linux, a modern DevOps pipeline, some tools from JFrog, and a handful of open source tools can make it really easy to deploy updates and security patches to your Edge devices, as easy as it is to any other application. So we can do better, y'all. Thanks for taking the time to listen to me today. I hope I brought you some useful information, or at least an interesting perspective. If you have questions, I will be around for the rest of the conference, but you can also hit me up on Twitter at Dixie3Flatline. And if you know what that username is a reference to, because so far only one person has gotten it, DM me and I will send you a t-shirt. You can also email me at catc@jfrog.com. And again, if you go to jfrog.com/shownotes, I will have this slide deck and links to all of the resources I mentioned up there. Thanks for listening. Enjoy the rest of the conference.